third we have done, huh? Is that true? Do you think so? Have you done it? We have done it. So there is one topic left. I told you that will be assignment for you. Reflection and refraction of EM waves. So you just study it from the book. So it will be the take home study. Okay? So you'll do it yourself. So I'll ask that in the examination at least. So till now what we have done, we have studied static electric field. Okay? Rather we have done static electromagnetic field, and we have done time varying electromagnetic field but without sources. Clear? We solved what electromagnetic waves we have arrived at without sources. Clear? Now let's try to figure out if your sources are present. Okay, let's say at some point. So you are having at some point some source. Let's say some charge density and some current. Okay, somewhere. Okay, so and now you need to figure out. Let's say at some time and later time. Let's say this is at some time t prime, and this is at time t. Okay, so you try to evaluate the field produced by these very charges. Okay, so it's a dynamical problem. Okay, so let's say you are having some source somewhere charged. Let's say a charge is moving somewhere, and you are supposed to calculate what is the electromagnetic field produced by that charge. Clear? So the charge is moving somewhere. Okay, you got my point?
Yes, sir.
So the effects what you will see from that moving charge, it will be at a later time. Okay, you cannot do it at instantaneously. I mean, you cannot. Okay, you have to do it from somewhere else. Okay, some point. Let's say you are think of these radiating sources. Let's say you are having sun. Okay, so you are having charges are moving there, and they are producing radiation all the time, and you are observing the radiation now. Okay, at this very point. So your source is sun, and you are observing that radiation now. Clear? You got my point. The radiation what you observe now, it's actually the radiation which has been generated sometime earlier. Okay, so if I calculate now, let's say the fields due to this kind of source which is far away from us, okay, we call such fields as the retarded fields. Clear? Because you measure something now which has happened earlier. Clear? So that's our problem. Okay. Yes. Now let's start with the wave equation. Okay, let's start with inhomogeneous Maxwell's equation for the time being. So this is our inhomogeneous Maxwell's equations. It contains sources, is it? Now in the previous case, J nu was 0. Okay, then this was simply you had thus the homogeneous equation. Wave equation was homogeneous. Now we'll assume non-zero J. Okay, it means currents and charges are there. Okay. Okay, so let's work out this thing. So it is like this. Clear? So this partial mu, it is the box operator, the DLM version minus partial mu. I can interchange the two, so it will be partial mu E mu, okay, like this. Clear? So now we apply the Lorentz gauge. Okay, by the way, this Lorentz is not the same as the person who has derived Lorentz, is it? It's not this one, huh?
Yes, sir.
So Lorentz here is not equal to. Okay, so this is some other guy who has proposed this gauge. It's not the same who has actually derived, the Lorentz transformation. So we'll put like this. I have not told you till now, but yesterday it occurred to me. So I should told you it's Lorentz gauge. So I am having in Lorentz gauge this part. Okay, so now this is an inhomogeneous differential equation. For each component mu, you are having differential equation. Clear? So we can do this because it's an inhomogeneous differential equation. We can solve it by method of Green's function. Clear? Okay, before doing that, let's try to do it in a simpler fashion. Okay? So let's convert this into the three-dimensional form. So separate out the components. So this equation turns out to be, can anybody? Nebula square A minus 1 by C square. So this we have already written, minus 4 pi vector C vector J, and you are having nebula square phi minus 1 by square. Okay, so that's equal to minus 4 pi. So these are the two equations and they form, okay, how to do it. So you are having a source term on the other side. How to figure out the solution of this very differential equation? We'll solve one. Let's take this very equation. We'll solve. Is the form of the equation same? Yes, sir. That is same, except of the factor you are having j here, you are having rho here. But that means call this as a function f. This is same as the function f. Clear? Okay, so you are having the same inhomogeneous differential equation. Now let's try to solve it. How to do it? How we solve an inhomogeneous differential equation? Anybody? We have been doing it. I mean, how to do it? Tell me. So you solve. Okay, so let's say I am having this very equation, nebula square phi minus 1 by square. So let's try to solve this very equation. How I can do it? First tell me. So in this, okay, I need to figure out. Anybody? How to solve this inhomogeneous differential equation? Forget about you are doing electrodynamics. You are having an inhomogeneous differential equation. What is the solution of that inhomogeneous differential equation? Second order linear inhomogeneous differential equation. What is the solution? Yes? It is the sum of the homogeneous part and the particular integral, is it? So you solve it for the you can figure, there are two parts of the solution of an inhomogeneous differential equation. I have been telling you all the time in this very course how to solve these things. So first thing is you solve it for the homogeneous part. You figure out the first homogeneous part, and second is figure out the particular integral part. Okay, and how we do the particular integral? You solve it for a point charge or a point source. Okay, then sum up the because of the linear superposition principle, then get the contribution from all the things. Okay, so how to do? Okay, let's do it. So you are having, okay, first thing is solution contains what? A homogeneous part plus a particular integral part. Okay, we are interested actually in this particular integral because particular integral is related to this inhomogeneity. Clear? Okay, so what I will do, okay, now it's a time dependent problem. Okay, you should understand it. It's a time dependent problem. So let's say in certain volume, let's say you are having some volume V here. Okay, so in this very volume, charge density is defined. Okay, you got my point. Okay, so there is actually the motion involved, or dynamics is involved in this very case. Now what you do? How to? Okay, you solve this equation for a point source. What is the point source? How to figure out the point source? That means instead of the charge density, you put a point charge density. Oh, remember, okay, so you have, if you remember, LXL. So you solve it for, if you are having LX, let's say some y is equal to some f of x. How do you do it? So you solve it for some function for a point source. Is it? So this delta x means a point source. Clear? So how to do it here? Okay, how to do it here? Now let's discretize this very volume, okay, into a smaller parts. Let's discretize this very volume in. This is the way how we can do it. Okay, you pick up a smallest part, a very small part. Let's take this is the small part. Okay, this very region. Let's assume the charge carried by this very region is dq. Okay, so what is the total charge?
Q.
Let's say it. Okay, the total charge will be simply q. So integral of this dq. Okay. Now tell me about this. Does this dq depend on time? It is at some instant of time you say the charge element, okay, in this very region is dq. Okay, so but after some instant it will change. Okay, I am slicing this very region at certain instant of time and figuring out how much charge is contained in this very volume. Okay, you got my point. So that means each contains this amount of charge. Let's assume you uniformly cut this very volume into the pieces such that each element contains the charge dq. Okay, so but as the time goes on, so this dq can change. Okay, but the total charge in the system remains constant, conserved. Clear? So okay, so let's call at certain instant of dq. Now what I will do, I will calculate the field due to this dq. So let's calculate the field due to this dq. Then, but my problem is to calculate the field due to this whole distribution, is it? Then how I can do it? I will simply apply the linear superposition principle. Calculate the field due to all these dq's, okay, as a linear sum. Clear? So let's do this very thing. So what is now the charge density? So the charge density here. So I will instead solve this very problem. Okay, so what it will be? Minus 4 pi dqp. Let's assume it is constant, okay, at some point r. Okay, so where r is the distance from the origin to this very element. Clear? So is this how we write the charge density? What is the charge density here then? So in this very case, what is the charge density? It is simply dq of p, okay, delta r. So it's actually a three-dimensional delta function, huh? Okay, because that is a three-dimensional problem. Huh? Clear? This is a point charge, is it? Now how to solve this very equation? Tell me how to solve this very equation. So this is a point charge now, is it? Is it a point charge? So what is the field due to a point charge? It is spherically symmetric, is it? So that means field will depend only on what? R. Okay, it will not depend upon the angular coordinates. Clear? So that means I can convert this Laplacian into the spherical polar coordinates, is it? So what is the Laplacian? So this will be simply 1 by r square partial by partial r, because I am using the radial coordinate r. So it is r square partial phi by partial r, okay, minus 1 by c square partial 2 phi by partial t2. Call this as equation first. Okay, so now let's try to solve this very equation. So for every, okay, for every r not equal to 0. So let's take the point. All the r, okay, so look here. So when you take r equal to 0, so this is blows up, is it? So r equal to 0 means you are at the center of the charge, is it? So, but let's take r not equal to 0. What will happen to this delta function? It is 0, is it? Is that true? So when I take r not equal to 0, what will be the equation? So it is, so that means I will be solving this very equation for a region where r is not equal to 0. In that case, so it is equal to 0. So I have, this equation is reduced to a homogeneous equation. Clear? Samajh aa? Okay. So now let's differentiate it. So what you will get? So you will get partial 2 phi by partial r2 plus 2 divided by r partial phi by partial r minus 1 by c square partial 2 phi by partial Q2 is equal to 0. So it is a region where R is not equal to 0. This is our equation. Clear? So now let's simplify it. So you are saying I want to remove this linear derivative. Okay, first order derivative. Okay, so you are having second order derivative here, second order derivative here, but there is this kind of odd term with a first order derivative. Okay, let's eliminate it. How to do it? So let me introduce a function. Let's write this phi to be some chi by r, where chi is unknown. I don't know what is the value of this chi. Okay, clear? Okay, so let's substitute. Okay, so let this phi, so I can have partial phi by r. So what that will be? So it is minus 1 by r square chi plus 1 by r partial chi by partial r. Now let's take this second derivative, partial 2 phi by partial r2. So it's minus, now tell me, so it is plus 2 by r cube chi minus 1 by r square partial chi by partial r, okay, plus, okay, so it is minus 1 by r square partial chi by partial r plus 1 by r partial chi by partial r. So how much is that? So it is 2 by r cube chi minus 2 by r square partial chi by partial r plus 1 by r partial 2 chi by partial r. Clear? So now let's substitute these things. Okay. So you are having from that very equation what you will get. So now tell me, for partial 2 phi, okay, what you will get? So you will get simply partial 2 chi by partial r2 minus 1 by c square partial 2 chi by partial t2 is equal to 0. So you substitute for phi and t as well. So 1 by r will come out, 1 by r square. So clear? So ultimately you will get this very equation. Is it? So do you feel it is the same, the one-dimensional equation we have solved earlier? Do you feel so? Do you feel so? What going here? Do you feel so? It is the same equation what we have solved it? We have solved it some time back? Huh? Do you think so? Huh? So what is the solution here? So no, solutions are of the form. Can you tell me? So chi is actually of the form f1 of t minus r by c plus f2 t plus r by c. So this we have already solved. Okay? And now tell me what is this very wave? So this is a wave that's moving outwards, and this is a wave that's moving inwards. Clear? But since we are observing our source from far off distance, clear? So that we will be interested in a solution that moves outwards, which is moving radially outwards. Okay? So in that case, we can discard this very solution. Clear? So we are not interested in this very solution. We are only interested in this kind of solution. Okay? Since you are observing a source from far off distance, not from okay other distance, clear, from some distance, okay, and you will always observe an electromagnetic wave coming out of that very source. Clear? Samajh aawa? So in that case, this will be the this will represent our physical situation, but this will not. This means simply you are observing a wave which is moving towards the source. Clear? So we are not interested in this thing. Okay? So we'll discard, in this case, we'll discard this f2. Therefore, I can write this phi, okay, discarding f2. I will write this phi to be, okay. Okay, so what is this phi? So it will be simply chi. Since chi is a function, okay, so it's f1, is it? T minus r by c, it means, so chi is actually function of t minus r by c. So I will introduce that kind of solution. So it's not multiplication, it is function, divided by r. So what is unknown to us? Chi. So we have figured out what is the form of chi, is it? So it has to be the function of t minus r by c. In other words, it has a function of r minus ct, ct minus r, the x minus ct, what we have done earlier. Clear? Clear? Okay, so now let's try to figure out what is this chi equal to. Okay, let's try to understand it. Okay, how to do it? Okay, So we will match, since we have solved our equation for r not equal to 0. Clear? So let's try to match our solution when r tends to 0. Clear? So what will happen? So think of the, let's say, think of the potential due to point charge. How much is that? That depends on 1 by r, is it? So if r tends to 0, what happens to the potential? It blows up, is it? So it increases very rapidly. Clear? Okay. So now let's take r tends to 0. Okay, if I take r tends to 0, so what will happen to these very terms? So these terms, okay, so these terms will be larger, is it? So in this very equation, so this will be, these two terms will, okay, so they will grow rapidly. Clear? So they will tend to infinity rapidly. What will happen to this very term? Okay, so this will be a slow function. Clear? So there isn't any r. Okay? Clear? So that means as r tends to 0, okay, so the magnitude of these very terms is larger than the magnitude of this very term. Clear? So in that case, we can ignore this partial 2 phi by partial 2. Clear? So you got my point? So everybody, okay. So when r tends to 0, so these terms are very large, is it? Instead of this very term. But if you see, it is actually this very, okay, so this comes from, so you are having this nebula square phi minus 1 by c square partial 2 phi by partial t2 is equal to minus 4 pi dq of t delta of r. Is that true? Okay, so now look at this very equation. You have this equation at hand. So when r tends to 0, so this grows very rapidly and the magnitude of this term becomes small in comparison to this thing. Okay, so in that, okay, I can ignore this term safely. Okay, so what remains there? So from this very equation, what remains? So I am having this nebula square phi. In that case, so it will be minus 4 pi dqt delta, because r tends to 0, so this will not be vanishing. So r tends to 0, so because it blows, so it will not be vanishing. So now you are having a Poisson equation for a point charge, is it? So what is the solution? Now tell me, what is the solution for this very point charge? So in other words, you are having simply, tell me, this phi, so you will be having Coulomb's law simply, dq t by r. Is that true? Is this the potential? Yes. So now take, so if you, okay, so let's apply this phi to this very equation. So it will be dq by dr, dq t by r, okay. So nebula square 1 by r gives you minus 4 by delta of r, dq t cancels. So this is a solution to this very equation, is it? Clear? Is this a Coulomb's law? Yes. Okay, so at r, when r tends to 0, this law is valid. Clear? So now I want to match now the solution when r tends to 0. So this solution should match, is it? When r tends to 0, this solution should match. You are having 1 by r function. This phi is a function of 1 by r, is it? Yes, sir. Is it? So what is this phi? So in this case, 1 by r. So that means when r tends to 0, this chi must go as what? dqt. In other words, I can say, okay, so in other words, okay, we can write this chi simply is dq. Okay? So chi is simply our what? This small charge. Okay. So now let's write then the solution in the entire domain. So therefore our solution is this phi is equal to dq. So it is, this dq has been evaluated at what time? T minus r by c. It is actually the retarded time. Okay? So now this is the potential due to a point charge. But we are not interested in the point charge. We are interested in the charge distribution. Clear? Rho, is it? So now let's write that. So then how to do it? Anybody? Just tell. So what is the charge distribution? Let's write rho, is it? Okay, now so how to do it? So it means I can write this potential. Okay, the solution to our problem is this phi naught, the homogeneous part, integral of what? Rho of P minus R by C divided by R d. Where you are integrating over a volume where the charge is defined, is it? So, samajh aa? You got it? It's simply the superposition. Have you got it? How we can define the charge density? Okay, so look here. So you write rho is equal to so if charge is given, okay. So let's say you are having charge density given. Now let me calculate the small charge dq. What it will be? Rho dv, is it? So how I can write? If dq is defined at T minus R by C, what it will be? Rho of P minus R by C dv. Clear? Okay, so what is the total charge? Q. Okay, so you need to integrate it, is it? So I am calculating the field due to this charge, okay? Now I need to integrate it, okay? So let's integrate it. So let's integrate this very. So you will be getting actually integral of dq T minus R by C by R. Is that true? What is dq? So it's actually rho of T minus R by C dv by R. Clear? So samajh aa? Okay. So in other words, so this is our, okay, so this is the inhomogeneous part. So we call this phi as a retarded potential, retarded phi, okay? Since phi and this A has the same form, clear? Differential, they satisfy the same kind of differential equation, then I can similarly write this value of A, clear? Samajh aa? Any question? Just tell me. So I'll write this phi. Okay, forget about the homogeneous part. Okay, so I'll write this phi is equal to integral of rho of T minus R by C divided by R dv. So that is same equal to, so let me write this shorthand notation R dv. Okay, so similarly we can write this A, vector A, because there is only 1 by C is the difference. So it is, anybody? So it will be this current density J minus R by C divided by R. So that is 1 by C integral of J minus R by C as a subscript. Okay. So we can put it in nice form this way. Let's put it. So while I am integrating, tell me. You are integrating over a volume where this charge is defined, okay? You are not integrating over the volume where you are observing it. So there are 2 points. One is the point of observation and another is the point which you are observing, okay? Where the charge is given. Huh? Okay, so let me draw a diagram, simple diagram. Suppose at some point you are having a, let's say, you define certain coordinate system. Some coordinate system, let's say, so this is a coordinate system. At some point, at some time, earlier time, this charge density is given. Okay, so let's call this as you are having the volume V prime. Okay, you got my point, and you are observing it here. Let's say at some another volume at some time t. Okay, so at this very point, this is the observation. So this is the point of observation. And this is the point where you are having charges and currents. Clear? So let's call this point. Okay. So this will be some, let's say this is your R prime and this is your R. So this will be R minus R prime. Clear? So samajh. So in that case, now what is our volume? I have defined it volume V prime, okay? Got my point? So therefore I will write. So this phi at the point r and some time t. So the phi which I am determining at this very point, okay? So what is that equal to? So that's equal to rho of, anybody? Anybody? Huh? So now tell me, so you are having a electromagnetic, let's think a signal, okay, an electromagnetic wave, so it will propagate to this very point, is it? So how much time it will take? So if you are having earlier time t prime and final time t, how much time it will take? T minus t prime, okay? So what is the distance it will cover? C times this thing. So how much is that equal to? R, okay? So now let's solve this thing. So, okay, Ct. Okay, so you can write t minus t prime is equal to r by c, clear? So what is t minus r by c? So that's equal to t prime. So this equation is having one solution. For every time t, it's having one solution, is it? So you need to figure out what is your earlier time, clear? Oh, samajh aaya? So that means I need to define what is the charge density at earlier time, clear? So let's write that as r prime and t prime, okay, divided by r, so of t, let me write like this in r of t prime, because they depend on time. This will change, okay? So d3 r prime, so it means I'm integrating it here, okay, where this r prime and t prime, they are related by, so t prime is equal to, so t minus r by c, clear? Got it? So now look here, the time component, what is happening to this t prime? After what is happening to the, okay, t prime? So that is t minus r by c. So it's a retarded thing, okay? So, or in other words, you are measuring this thing at the earlier time, okay? So what has happened at the earlier time that you are measuring now, okay? Okay. Similarly for this E. Everybody got it? So have you got, so this is actually the general idea how we can arrive at the concept of the retarded potentials, okay? So from this retarded potential you can calculate a retarded field, okay? So you can simply calculate the electric field if in some region this charge density is given. Okay, so these are very general formulas, clear? Okay, so now let's do this thing in a different manner, okay? So let's use the Green's functions. Okay, so what is our equation at hand? Let's take the Green's function method. Okay, so this is our equation. Box operator acting on. What is it? So box operator acting on. Is equal to 4 pi by c g nu, okay? So if I need to define the Green's function for this very objective, okay? So okay, let's take it for the one component. It holds for, okay, let's take it for the one component. Let's take mu equal to 0. So what you are having? Like this thing. So it is phi is equal to 4 pi rho. Clear? So let's take this very equation at hand. Now let's solve this very equation by Green's function method, okay? What I have to do? What I have to do? Just tell me if I have to solve this by Green's function method, what I have to do? What is the procedure? We have done Green's function in detail, okay? What is the procedure? Huh? What is the procedure? Molvi? Oh, Molvi, just tell me the procedure. By the way, why only few people have come? Okay, we introduce a function, okay, g of x prime, okay, such that this object acting on the g x prime. So this is a differentiation with respect to x. So that's why I will put an x here. So it's equal to minus 4 pi delta x minus x prime. Okay? Clear? So I'll introduce this function. So let me put in arrows here. So no. So it's a 4-dimensional thing, eh? So x is a 4-dimensional. So that's actually equal to minus 4 pi delta 3. Okay, this x minus x prime. Okay, delta t minus t prime, because it's a 4-dimensional object, eh? So that's I have to use a 4-dimensional this delta function. Okay, clear? So this is how we can do it. Okay, so now let's so I will solve this very equation. Now what is the method to do it? Anybody? So let me write this as a delta 4. Okay. What is the method? So just use the Fourier transforms. This we have done. So let's introduce a Fourier transform. So I will define g of x prime in 4 dimensionals. d4 of k, let's say, divided by 2 pi raised to power 4 e raised power anybody? Minus I k dot x minus x prime and g of p. Okay, where g of p is the Fourier transform of g. Okay, and let's write this 4-dimensional delta function. Okay, x minus x prime, that's equal to d4 of k by 2 pi raised to power 4 e raised to power minus I k dot x minus x prime. Okay, let's substitute it back in that very equation, in this very equation. So this is the differentiation with respect to x, is it? So what that is? Partial, this object is what? Partial mu. Okay, so when you act twice, so it will be minus I k mu, minus I k mu, minus and minus, plus I square, minus. So what you will be getting? So you will be getting minus this k mu, okay? Then you will be getting this g of p, that's equal to anybody? Minus 4 pi. Okay? So rest of the terms, I have skipped one step. Huh? So you have to substitute it, then cancel the terms. Huh? So this will give me, so this equation will give you this thing. So what this object is? So k mu is k square. So it is g of p. So that's equal to simply 4 pi or g of p, that's equal to 4 pi by k square. By the way, here, so in this k dot x minus x prime, so look here. So you are having, so all the variables here are linearly independent. This is a 4-dimensional integral. All, suppose k1, k2, k3 and k0. Okay, they are all independent integrals, clear? Unless and until we impose a condition between k's and k0. What does that mean? So look at this. K dot x minus x prime. Okay, what is that equal to? So it's k0, x0, x prime, is it? Yes. Then minus this vector k. Okay, forget about this x prime. So it's like this thing, dot x, clear? So what is that? What is k0? It is the energy of the photon, is it? Otisha? So let's write that as omega. What is this x0? So it is actually omega. X0 is time, is it? So it is t. Minus, what is k dot x? So it is as such. Clear? So look here. Okay. So you are having this object as omega t minus k dot x. Now look here. So if you are having k mu and k mu, I am saying this omega and k, they are linearly independent of each other. Okay? So if they would have been dependent on each other, then k mu is what? It is 0. What is k mu? It's k square. What is k square equal to? K0 square minus this vector k square. Okay, so what is that? Omega square minus simple k square, is it? So what that should be? 0 if they were dependent by this very relation. C is omega equal to ck. Clear? Oh, samajh aaya? Okay, in this very calculation, all these omegas and k's are independent of each other. We'll see actually their dependence will come when we evaluate the integral, this kind of integral. Okay? So samajh, for the time being they are all independent. Otherwise this is not satisfied. This because k it is a null vector if the condition is satisfied in free space. If omega is equal to ck, okay, the energy of the photon, so then k square is simply equal to 0. It is not valid then. So you are having 0 equal to 4 pi. That's an undefined quantity. Clear? Oh, samajh? That's a vague statement then. Wrong. Okay. So you should remember it. When you do some Fourier transform, let's say in d dimensions, when you just start with the definition of the Fourier transform in d dimensions, all the components in d dimensions are to have to be independent of each other. Once you get the Fourier components back and solve the integral, then you will see because of the integration certain components will be dependent on certain other components. Clear? We will see that. Okay. So what this object is? So it is 4 pi. So let's write it as k square. Okay. So it will be some k0 square minus vector k square. So how much is that? 4 pi divided by, so it is omega square by c square minus vector k square. Samajh aaya? Let's substitute it back. So if it would have been omega is equal to ck, so then this is equal to 0. So you are having poles, is it? So this will happen, okay, in a moment. Now, so let's write now this very g of x prime. So it is, okay, let me write d3 of x, d omega separately. So it is 2 pi 4. So there will be 1 by c here. Because c time, okay, dk is 0 is, what is k0? Omega by c. Sorry, k mu is omega by c and vector k. E raised power. So let me write g of p. So what is that? 4 pi. So I'll write that 4 pi here. Okay. So then you are having 1 divided by omega square by c square minus this k square. Okay. E raised power minus I. When you say, let me write k dot x minus x prime for the time being. Okay, now you are having poles of this integral. Where are the poles? So let's try to integrate over omega, is it? Forget about k. So let's try to integrate over omega. Okay, what are the poles? So if I integrate over omega, what are the poles? Okay, so poles are on the real axis, is it? So you are having poles are on the real axis. If we integrate over omega, okay, clear? So what is that? Let's say this is the omega plane. Okay, so this is imaginary of omega and this is real of omega. Where are the poles? So one pole is here, omega is equal to ck, and another pole is here, omega equal to minus ck. Is that true? So Samasha, now how to choose the contour? Clear? So Samasha, if I try to integrate over omega, let's say I need to choose the contour. Okay? When you solve such kind of integrals, choosing a contour means defining a boundary condition for the problem. Okay? The way you are choosing a contour along the real axis, okay, if you are having poles along the real axis, and the way you choose actually the contour to solve that integral, okay, it implies you are choosing a boundary condition. Clear? Samajh aaya? You got it? Since in electrodynamics we are dealing with the differential equation, means we are dealing with the boundary condition, is it? So choosing a boundary condition in this very problem means choose a suitable integral, suitable contour. Clear? So Samajh, how to do that? Okay. Can you tell me how to do that? So what kind of boundary condition we are interested in? So source is some distance away from us. what kind of boundary condition we should be dealing with? A retarded boundary condition. A boundary condition which gives us the retarded potentials. Clear? So what does that mean? So let's write this omega integral separately for the time being. So you are having d omega by 2 pi 1 divided by omega square minus c square minus k square. Okay, e raised for, now let's look at, so it's e raised for minus I k0, that is omega by c. Okay, then you are having x naught, is it? So that is c t minus t prime. Okay, so this c and c will cancel, it is simply omega t minus. Let's look at this very integral. What does that mean, the retarded boundary condition? Because omega contains t, is it? Time. Okay, so okay, what is this exponential? E raised for minus I k dot x minus x prime. So this is actually equal to e raised for minus I omega t minus t prime and e raised for I k dot x minus x prime. Clear? So I am just separating out the omega part. Okay. So now let's integrate. So what are the limits of integration? From minus infinity to plus infinity. Clear? It's an indefinite integral. That means you are integrating both whole things. So let me choose a retarded boundary condition. What does that mean? Since what we are looking for, Green's function, is it? So that means the Green's function. So it means Green's function for t less than t prime. What does that mean? T prime is greater than t. Since I am taking t prime to be earlier time, okay? So that means for time is earlier than t prime. Okay, I don't have the Green's function. So when I am saying the retarded boundary condition, so I am having, since Green's function represents me what? It is the solution of the differential equation. Clear? Solution of the differential equation means you are getting the potential, is it? So, and I am interested only in the retarded part of the potential. Clear? So what does that mean? The potential, what is the retarded potential? It is the potential defined for time greater than t prime. If t prime is earlier time, okay? Or the potential is defined for the new times, okay? Now you don't, in that very case, you don't have the potential defined for the time is earlier than t prime, okay? Because we are not taking that kind of solution. If my t, let's say t prime is earlier time, if before that t prime I don't have any kind of solution, okay? What does that mean? There are no Green's function in that case. So that's exactly the retarded boundary condition. In that case, Green's function for t vanishes. So what does that mean? G of x prime, so that's equal to 0 for t less than t prime. Okay? So, now I need to choose the Green's function for t greater than. How to do that? Okay, on the contour, how to do that? In that case, what you do, you push your these singularities, these poles to the lower half plane. Okay, since what is t less than t prime? So, okay, so look at this very exponential. So when you solve an integral along the real line, okay, when the poles are along the real axis, you always look for the Jordan lemma, is it? So Jordan lemma on the larger contour should satisfy, is it? The integrand should vanish on the larger contour. You remember Jordan lemma? So how it will happen? So this factor should be damping, a dampened factor. Dampened factor means e raised for minus x type. So let's say x tends to infinity, that means contour stretch to infinity. So this term goes to 0. Okay? So only you extract the values from these poles. So Samushiva, you got my point? So there are two ways to choose this kind of thing, two ways to solve this problem. Rather 3 ways, I will define only 2 ways here. So either you choose a contour in the upper half plane or the contour in the lower half plane. Clear? So since what kind of boundary condition I am having? Retarded boundary condition. So I will choose okay, I will push these poles to the lower half plane. Clear? So we will push in this case. So why that is important? Now look here. So when t prime is, okay, t prime is greater than t, it is e raised for minus I omega t, is it? T prime, so it will be positive factor, is it? So what will make it to damp? Okay, so when t prime is greater than t, so what it is having? So exponential is that e raised for I omega t prime minus t, is it? So this is now a positive factor, clear? So what it will make it damp? So tell me, when it can be 0? So when this t prime minus t, it is a negative value. Okay, so that means, so when it is having a negative value, so I need to choose in the lower half contour, is it? So since this is a positive quantity, if it is, let's say, minus I, sorry, it should be equal to I. So then it will be e raised for minus omega. So in that case, I am choosing the upper half plane, is it? So and what will happen to this value? When contour stretch to infinity, it will go to 0. Okay, so now let's do it first, then you will appreciate the result. What exactly I mean by that? Okay, so let's do it. Let's push these poles to this lower half plane, okay? So what I will do, I will push them here. So what it will is omega minus ck minus, let's say, I delta by small amount, okay? So what it will be, omega equal to ck minus I delta, okay? So I am pushing these very poles here in this very case, correct? So we are in the retarded boundary condition, clear? So let's choose now the contour in the upper half plane, okay? So what I have done, I have pushed my poles where? To the lower half plane further. Okay, so you will see in a moment what it means. Now let me choose a contour here. So this is our contour. Okay, so now does this contour involve any greens, sorry, any poles now? So there are no poles with this, because poles are where? They are shifted to the lower half plane. So that means, so this will give me 0. If I integral this very thing, it will yield me 0. Okay, so in this case, when it will happen, what will happen? So in this case, actually, t is less than t prime. So in this case, what is t? T is less than t prime. Okay, because, okay, so now let's take the lower half plane. Okay, in the lower half plane, you will be getting a non-zero because poles are where? In the lower half plane, clear? So let's solve this for the lower half plane then. So you people followed it, what I have done, what I am saying? Have you followed it? This is very tricky point. Have you followed it? Yes. Huh? Okay, look here, again, when you are having t prime, okay, so this is positive, then you can, okay, if you have pushed these up, these points, so that means this singularities, sorry, pole is shifted by I delta in the upper half plane, clear? In that case, this retarded will be 0 and we call this as the advanced part. Huh? So the retarded Green's function comes from the lower part of the evaluating the this integral in the lower half plane. Any problem? Okay, good. So let's work it out. So now we'll choose, okay, this is the contour of, so this is our contour. So it involves now both poles, okay? So what does it mean for this thing? Since I have pushed both the poles downwards, is it? So what does it mean? So this integral means, so this is actually equal to, sorry, minus infinity to plus infinity g omega by 2 pi. So there is actually what we call it the Feynman contour. So I will not do that. So it is e raised power minus I omega t minus t prime. So it is in the region lower half plane. So omega is shifted actually. Let's try plus I delta whole square by c square minus. So now you can check where are the poles. Okay, both are down, is it? I just shifted the energy value, the omega value, because we are in the omega plane. So you are simply changing the omega value, is it? You are not changing the k value. You are simply changing the omega value. Now let's work it out. So you do the partial fractions. Okay. So this will be the assignment. Use partial fractions. So that means you have to put, this is actually 1 by x square minus a square. So you put it as 1 divided by x minus a plus 1 by x minus plus a, is it? Samajhan? So in that way you will be having this as a sum of two integrals. Okay, clear? Shall I write the result directly now? Shall I write? Okay, so you will be having, okay, so can you tell me what will be the value of the integral? Anybody? So let me substitute it directly here. So it will be actually, okay, so use the value of this very integral. So what we will get? G retarded Green's function, this x prime, that's equal to minus, it will be minus I by 2 pi square okay, yes. So can you do it? This is a very simple integral. So it will be actually integral will be of the form of, so one term will be actually e raised for minus I kc t minus t prime, another will be another part e raised for I kc t minus t prime kind of thing. Okay, divided by k, so there will be 1 by k, like this. Okay, so now you can see directly. You are having two poles, just put the value there. What is the value of omega? Ck. So in one case you put the Ck, in another k you put minus Ck. Clear? So these are only the two values. So actually what I try to say, how we treat these integrals. They are not very simple integrals. They are very tricky integrals. Okay, you cannot do directly. Okay, so you will be getting this kind of factor 2 pi square. Okay, so d3k e raised to minus I kc t minus t prime. Because you have done actually complex analysis in depth. So that's what. So there plus I vector k dot x minus x prime. Okay, minus e raised to I kc t minus t prime plus I vector k dot x minus x prime divided by k. What is your problem? So everybody followed it, what I have done? Okay. So now let's, okay. So this integral is very simple now. So you are having integration of k, so you are having k here, is it? So you cannot take this very factor out. Okay? For Samashavan? Okay. So what you will get, so it is minus I divided by 2 pi square. So you will write it. Okay. So 0 to infinity, k square dk. Okay, then you are having d theta sine theta 0 to pi, then integration over phi 0 to 2 pi d phi. Okay, and this very integral. Okay, clear? So this is the integration. d3k is what? K square, because there is a spherical symmetry involved. Look here. So you are having k dot here. Samajhama? So you have only the theta dependence of this integrand, is it? So that means you can do now the spherical polar coordinates. Clear? If it would have been, let's say, if it is not a theta here, let's say you are having kx here, ky and kz explicitly specified, then you have to do first the integration of, let's say, kz, then ky, then kx. Okay, then you cannot write it in this fashion. So you can now write it in this way. So first there is no phi dependence. Once you integrate over phi, it will give you 2 pi, is it? So then you are having d theta sine. I will not evaluate this very integral. These integrals you have been doing. So then you are having d theta sine theta. Look here, you are having kc t minus t prime, is it? Plus I k dot. So it is, let's write this r as, okay, magnitude of x minus x prime. Let's write it, this magnitude. So what this will be, k dot. So k dot x minus x prime will be equal to simply k r cosine of theta. Then you put, let's say, r cosine of theta, you can put equal to sine of theta. Okay? sorry, x. You can put r cosine of theta as z. Then differentiation will yield you this sine theta, and the theta will go here. Is it? So much even. So then you will integrate over that very variable. Clear? So by the way, you are having k square here. 1k and 1k will go. So once you integrate over theta, then that means, let's say it will be dz minus 1 plus 1 dz e raised power minus I k. Okay, something. Okay. You can put, let's say, kr cos theta some value equal to z. Then you are having integration over that theta. Okay. Oh, sorry. What I am saying. So you are having only integration first along this thing. Theta is here, is it? So you will first integrate over this thing. Okay. So then you will be getting in the denominator 1 by k. That k will cancel with this thing. You will be having then only the function of k. Then you integrate over k from 0 to infinity. You will be getting, actually, I will write that final integral what you will be getting. Okay. So you will be getting this kind of thing. So once you do all these things, 2 pi r. Okay, there will be 1 by r factor. Okay, but look at these factors carefully. 1 by 2 pi. Okay, so you'll be getting minus infinity to plus infinity. So you'll be getting a dk. Okay, so you'll be getting like this thing, 0 to k. E raised power minus I. So this I will work out myself. This thing k c t minus t prime minus r. Okay. Then you have a minus e raised power minus I k c t minus t prime minus r. Then you have a minus e raised power I k c t minus t prime minus r. Okay. Sorry, this is plus r. This is plus r. Then you have e raised power I k c t minus t prime minus r. X. Okay, so let me tell you here. Look at this thing. So this is an integral from 0 to infinity, is it? Now you are having 0 to infinity e raised power exponential. So it's like this kind of integral, 0 to infinity e raised power I kx plus minus I kx. Okay? Let's say dk. So what is the value of this very integral? Anybody? So it's proportional to delta function. It's something delta function plus principal value of the integral. Have you heard about that identity, Dirac identity? Huh? So it's something, okay, pi delta x, okay, minus I, principal value of 1 by x. Is that true? You know it? Forget about it. If you don't know, forget it. Okay? You don't need to do it. Okay, now look here. So look at this very term. You are having minus ik here, is it? So look at this thing. What you are having? Plus ik, is it? Now in this very term, if I change k to minus k, so what is the limits of integration? 0 to, look here, I will not be doing it. Okay, if you change, okay, you are having 0 to infinity and k is here. Let's change k to minus k in this very thing. What will happen to the limits of integration? Minus infinity to 0, is it? So if you change in this to minus k, so the limits will be what? Minus infinity to? It will become the same term as this thing. So then you are having minus infinity to 0, 0 to infinity of this very term. Clear? So one term you will be getting, okay, minus infinity to plus infinity e raised power minus ik c of t minus t prime minus r. In the other case as well, here you change k to minus k. So what will happen? Minus infinity to plus infinity, the same thing. So you will be getting another integral minus, okay, rather that will be actually plus. Yes, that will be plus. So here you change here k to minus k. Okay, so it will be minus infinity to plus infinity e raised power I k c of t minus t prime plus r. Okay, so now what is this? What is the value of this very integral? It's a delta function. Clear? So samajh aawa? So these are two delta functions. So what is our Green's function then? So our retarded Green's function is, okay, x t x prime t prime, that's equal to minus 1 by r. Okay, so one integral will be actually delta c of t minus t prime minus r. Okay, then you are having minus delta, sorry, it will be minus minus delta c of t minus t prime plus r. We are done actually. So It's almost done. Now look here. This delta function forces C of t minus t prime is equal to R, is it? So this delta function forces what? C of t minus t prime equal to minus R. So this will give actually you the advanced part. Since we are only in the retarded Green's function, is it? So we can discard this thing, yeah? Okay, so this gives you what? T prime is equal to t minus R by C, and this gives you what? T prime is equal to t plus R by C. Teacher? You got my point? So that means, so we can ignore it, right? And discard this very term. Discard this thing. So what is our retarded Green's function? So G retarded, okay? So this x prime, that's equal to minus delta C of t minus t prime minus, okay? So let me write magnitude of R is like this thing, yeah? Divided by magnitude of x minus x prime. So these are the four vectors on this inside. It is x and t, yeah? So now you can use, okay, we'll use it in the next lecture, yeah? Clear? So do all the integrals yourself. Okay, just fetch me the gap.